Somewhere in the universe tonight, two specks of matter are linked so deeply that touching one stirs the other, even with a galaxy lying between them. No one fully knows how. And tonight, we will explore why. This is the story of entanglement, the strangest idea in all of physics. Even Einstein called it spooky, certain it had to be wrong, and a century of patient experiment has shown it is simply, quietly true. Let the words move at the pace of your breathing. If your eyes are heavy, let them close. You can drift away and return anywhere, and the mystery will still be here in the dark. So settle in, my friend, and let the world go soft. Picture two coins spun at the very same instant in two different cities. In our ordinary world, each one tumbles on its own. One lands heads in the morning sun of one city, the other lands tails in the evening of another. And there's no reason on earth they should agree. They are simply two coins, far apart, doing their own quiet thing. Now imagine a pair of particles instead, two tiny flecks of light or matter born together from a single event, then gently carried apart. You could place one in a laboratory here and send the other across the street, across the ocean, or, in principle, to the far side of the galaxy. And here's the strange and lovely fact at the heart of everything tonight. When you finally look at one and find it spinning, say, upward, the other, in that very same moment, is found spinning downward, always, perfectly, as if the two had agreed in advance. But they did not agree in advance. That is the part that kept Einstein awake. You might think there is an easy answer. Perhaps each particle simply carried a hidden instruction from the start, a little sealed envelope that said, "I am up" or "I am down," and we only discover the answer when we open it. That would be comforting. It would mean nothing strange is happening at all, only that we were ignorant until we peeked. For 30 years, many of the world's finest minds assumed something like this had to be true. It feels like common sense. And yet, slowly and carefully, experiment after experiment has shown that the sealed envelope picture cannot be right. The particles do not seem to carry their answers with them. The answer, in some real way, does not exist until the moment of looking, and somehow, when one is looked at, the other knows. Sit with how gentle and how impossible that is. There is no wire between them, no signal anyone has ever found, nothing darting across the dark to carry the news from one to the other. And the matching happens faster than light could ever travel the distance, which means no ordinary message could be doing the work, because nothing we know of moves faster than light. The two are simply somehow one connected thing wearing the costume of two separate ones. Einstein gave this a name. He called it spooky action at a distance, and he meant it almost as a complaint. He was so sure the world must be local, that what happens here can only be touched by what is right here beside it. That he believed this spookiness had to be a sign of something missing in our theory. He thought we would eventually find the hidden envelopes, and the ghost would dissolve, and the universe would go back to behaving itself. He was, as gently as one can say it about a genius, wrong. The hidden envelopes were searched for with extraordinary care in laboratories all over the world. They were not there. The spookiness is real. The connection is real. A century later, it is one of the most thoroughly tested facts in all of science, and it remains every bit as strange as the day he first frowned at it. What does it mean? That is the wonder we are allowed to rest in tonight, because no one can fully say. The particles are not sending messages. You cannot use the link to speak across the void. We will find no telephone hidden inside it, and yet the two are bound. Touch one, and the other answers, with no time passing and no space crossed. It is as if the universe, underneath the comfortable surface of distance and separation, keeps a quieter accounting, one in which far apart is not quite the absolute we always took it to be. There is something tender in that, my friend, if you let yourself feel it. We move through our lives believing in distance, the miles between you and someone you love, the cold reaches between the stars. We treat separation as the most solid fact there is. And here, woven into the smallest fabric of things, is a hint that connection can survive any distance at all. That two things once joined may stay joined in a way that no gulf can loosen and no silence can break. The particles do not know they are remarkable. They sit wherever they have been carried, holding their shared secret, asking nothing of us. One of them, perhaps, drifts in a sealed chamber in a basement laboratory. The other, perhaps, has been sent down a thread of glass to a quiet town 100 miles away, where the streetlights are just coming on. Neither has changed, neither has moved toward the other. And still, between them, stretched across all that ordinary distance, there runs an invisible understanding that the whole of modern physics has tried and failed to explain away. Two specks of matter, one unbroken bond, the dark between them, full and patient and quietly alive. Suppose you wanted to catch the universe in a lie. For a long time, the strange link between two distant particles had a perfectly reasonable explanation waiting in the wings. Maybe, people thought, the particles simply carry secret instructions. Two specks of matter are made together, and as they part ways, each one tucks away a tiny hidden script, a full set of answers for any question it might later be asked. When you measure one and the other matches, there is no magic in it. They are just two travelers reading from identical notes they were handed at birth. It is a homely, sensible idea, and almost everyone believed something like it. The trouble is how to test it. The instructions, if they exist, are hidden. How could you ever peek inside and prove they are there, or prove they are not? In 1964, a thoughtful Irish physicist named John Bell found a way. He did not need to open the envelopes. He found something cleverer, a way to make the secret instructions, if they existed, leave a fingerprint they could not hide. Here is the heart of his idea, told gently. Imagine two friends set to opposite ends of the earth, each placed in a sealed room. Now and then, the quizmaster in each room asks one of three simple questions, chosen at random, and the friend must answer yes or no. The friends cannot speak to each other. They are far too far apart, and any message between them would arrive too late to matter. If they had agreed on a plan beforehand, a shared script of how to answer each possible question, then over thousands of rounds, the pattern of how often their answers agree would have to obey a certain limit, a ceiling, a line that no prearranged plan, however clever, could ever cross. Bell worked out exactly where that line sits. It comes from nothing more than the assumption that each answer was already decided before the question was asked, and that one room cannot influence the other. Then he asked, what does the quantum world predict for two entangled particles playing this very game? And the quantum world sails straight past the line. The particles agree more often than any secret script could ever allow. Not by sleight of hand, not by a measurement error, but by a clear, calculable margin. When the experiment is run, and it has been run again and again with ever greater care. The real particles behave exactly as quantum theory says, and exactly as no set of hidden instructions ever could. Let that settle slowly because of what it quietly rules out. It means the comfortable story is wrong. The particles are not simply reading from notes prepared in advance. Whatever binds them is something deeper and stranger than shared memory. And here's where Bell leaves us with a choice, a real fork in the road for how we picture reality, and one no experiment has ever let us avoid. Either the world is not local, meaning that what you do to one particle truly does reach out and touch the other across any distance, with no time and no signal in between. Or the world is not definite, meaning that the particles genuinely had no answer at all until the moment of measurement. That which way is it spinning was not a fact about the world until someone looked. One of these two cherished ideas has to go. The universe insists on it, and to this day, no one can tell you for certain which one we must surrender. There is something humbling in this, and something almost beautiful. For most of human history, we assumed, without ever questioning it, that the things around us simply have properties, that the moon is there whether or not anyone watches, that a coin in a closed hand is already heads or tails, that the world is fully made before we arrive to look. Bell's discovery does not quite overturn that, but it presses a cool finger against it. At the smallest scale, the world seems to hold its possibilities open, refusing to commit, the way a held breath refuses to become either a word or a sigh until the last moment. What makes Bell's idea so quietly powerful is that it asks nothing of us but logic. He did not need exotic equipment or a finished theory of everything. He needed only to imagine a fair game and to follow the rules of counting honestly to their end. And from that simple honesty came one of the deepest results in the history of physics. A proof that reality, at bottom, cannot be both separate and settled. Something has to give. The experiments that finally confirmed all this earned their makers the Nobel Prize, decades after Bell first set down his careful little argument. He had handed the world a question so sharp it could cut through common sense itself, and the answer that came back was not the comfortable one. So tonight there is nothing to solve and nothing to fear, only a quiet thing to hold. Somewhere beneath the solid-seeming world, two particles are playing a game whose rules forbid every easy explanation, and they go on playing it perfectly, in the dark, with no plan and no script. The line that no secret could cross, they cross it gently every single time. And the universe, keeping its deeper accounting, simply lets them. You could spend your whole life trying to send a message this way, and you would never succeed. It is a natural dream. If two particles are linked across any distance, if touching one truly stirs the other in the same instant, then surely you could use that link to whisper across the void. Tap out a code here, read it instantly there, and beat light itself across the galaxy. A telephone with no wires and no delay, reaching from one end of the universe to the other in no time at all. Generations of clever people have looked at entanglement and felt the pull of exactly this idea. The universe, with great gentleness, says no. To see why, picture what you would actually hold in your hands. You have one particle of an entangled pair. A friend far away has the other. You measure yours, and what you find is simply a result. Spinning up, perhaps. You measure again with a fresh pair, and this time it is down. Again, up, again, down. To you alone in your room, the results look like nothing but a long, patternless coin flip, pure randomness with no message in it anywhere. Your friend far away sees the very same thing, their own private stream of ups and downs, random as falling rain. Here's the quiet trick of it. Each half of the pair, looked at on its own, is perfectly random. Nothing you do to your particle can nudge your friend's results toward more ups or more downs. You cannot steer them. You cannot bias them. From where your friend sits, their stream of outcomes looks exactly the same, whether you are measuring your particles or have wandered off for tea. There is no remote handle to pull. So where does the famous connection hide? It lives only in the comparison. If you and your friend later sit down together, once you have carried your two lists to the same table, by ordinary means, at ordinary speeds, you discover that whenever you got up, your friend got down again and again in perfect lockstep. The agreement was there all along, but it was written in invisible ink that only appears when the two halves are laid side by side. And to lay them side by side, you must send your list to your friend the slow way, by letter, by phone, by light. Nothing about the meeting can outrun light, because the meaning was never in either list alone. It was always in the pairing. This is why the dream of the instant telephone quietly dies. The link is real, and it is faster than anything, but it carries no message, because neither end can shape what the other sees. The coordination is perfect and useless in the same breath. You may know the moment you look what your distant friend will find, but you cannot make them find one thing rather than another, and so you cannot tell them anything at all. There is a deep relief hidden in this, if you follow it far enough. The faster-than-light dream, taken seriously, would unravel something precious. Our entire understanding of cause and effect, the comfortable sense that causes come before their effects, that the past shapes the future and not the other way around, rests on the idea that no influence outruns light. If messages could travel instantly across any distance, that orderly flow of time could tangle and knot in ways that make a mess of the whole world's story. And so the universe seems to have arranged a careful, almost tender balance. It allows the spooky connection. It allows two distant things to share a single fate. But it locks the door against ever using that connection to send a word. And in doing so, it protects the gentle one-way flow of time that lets a story have a beginning and an end. Sit for a moment with how strange and how exact that balance is. It would have been simpler, you might think, for the universe to forbid the connection entirely, or simpler still to allow the messages to, and let the consequences fall where they may. Instead, we have something poised precisely on the edge, a bond that is utterly real and utterly silent, faster than light and yet mute, as if nature wished to show us that distance is not the final word, but would not let us turn that secret into a tool. Some part of this feels almost like a kindness. We are given a glimpse of a deeper unity, of a world more connected than it looks, and we are spared the chaos that would come if we could reach through that unity and pull. We get the wonder without the wreckage. So there is nothing here to chase tonight, and nothing slipping away. Two particles share their hidden agreement far apart, and the agreement keeps its silence. You could hold one in your hand and know in the instant of looking what waits at the other end of the world. And still, you could not send so much as a single word along that thread. The connection simply rests there, complete in itself, asking to be wondered at rather than used. Faster than light, and quiet as snow. Before you look, a particle is doing something we have no honest word for. We like to say it is in many places at once, or spinning both ways at the same time, and those phrases gesture at the truth without quite capturing it. What the mathematics describes is gentler and stranger than that. The particle is spread out across its possibilities like a wave spread across water, a smooth blend of here and there at once, each possibility carrying its own weight, all of them real at the same time, none of them yet chosen. Physicists call this a superposition, and for anything left undisturbed, it is the most natural state in the world. It is how things are when no one is looking. Then you look, and in that instant, the spread out wave is gone, and in its place is a single, ordinary fact. The particle is here. It is spinning up. One possibility has become real, and all the others have simply vanished, as though they were never there at all. This sudden change, from a soft cloud of maybes into one hard yes, is the deepest unsolved puzzle in all of quantum physics. And the strangest part is not that it happens. The strangest part is that no one can tell you what makes it happen, or even what exactly counts looking. Here's the trouble, laid out plainly. We have an equation, one of the most successful in the history of science, that describes how the wave of possibilities flows and spreads and ripples through time. It is smooth, elegant, and utterly reliable. But that equation describes only the spreading and contains no moment of snapping, no instruction that says, and here the cloud collapses into a single answer. Left to itself, the wave just keeps blending gently forever. The sudden choice, the single outcome you actually see, the mathematics does not say when it arrives or why or by whose hand. So we are left holding a question that sounds almost childlike and has no agreed answer. What is a measurement? Is it the moment a particle strikes a detector? But the detector is made of particles too, and the equation would simply have it join the spreading wave, becoming a blur of clicked and did not click together. Is it when a photon bounces off and carries the news away? But the photon, too, is just more quantum stuff, and it should blend in just the same. Follow the chain outward: particle, detector, photon, the air of the room, the eye of the watcher, the watcher's own mind. And at no link in that chain does the mathematics on its own draw a line and say, here the maybes end and the fact begins. And yet somewhere, somehow, they do end. You only ever see one world, one outcome, one definite thing. The cloud always, in the end, becomes a coin that has landed. This gap has a name among physicists: the measurement problem, and it has been argued over for the better part of a century by some of the most careful thinkers who have ever lived. Several serious answers have been offered, and it is worth saying clearly that none of them has been proven, and reasonable people still disagree. Some suggest there is a real physical collapse, a genuine snapping that the equation is simply missing, waiting to be discovered. Some suggest that nothing ever truly collapses, and that all the possibilities go on existing, each in its own unfelt branch of reality. Some suggest the whole question dissolves once you think carefully about what it means to be an observer made of atoms inside the very world you are observing. These are not idle daydreams. They are taken seriously, worked out in careful detail, weighed against one another by people who have spent their lives on the question. But they remain interpretations. Different stories told over the same flawless mathematics, and no experiment yet devised has been able to tell us which story is true. There's something wonderful in admitting that. We have a theory that works perfectly. We can use it to build the screen you are not quite looking at, to time the satellites overhead, to predict the behavior of matter to a precision almost beyond belief. It never fails us, and we do not know what it means. We are like someone who has been handed a key that opens every door and who can feel, turning it in the lock, that they do not understand the shape of the key at all. Perhaps that is the right note to drift off on, not frustration, but a kind of soft astonishment. The world lets us use it long before it lets us understand it. The particle, before you look, is a wave of quiet possibilities. The particle, after you look, is a single plain fact. And the crossing over between those two, the most ordinary thing in the world, happening trillions of times in every blink, is a mystery that the finest minds of 100 years have not yet been able to name. Tonight you do not have to name it either. You can simply let the question float, unanswered and unhurried, the way the particle itself floats before anyone arrives to ask it which way it is turning. A cloud of maybes, hovering in the dark, in no rush at all to decide. Physicists have learned to move the very identity of a particle from one place to another, while the particle itself never goes anywhere. To feel how odd this is, think first about what a particle's identity even is. It is not the little speck of matter so much as the precise way that speck is, the exact tilt of its spin, the full quantum condition it is in, every detail of its state. You might think of it as the particle's signature, or if you like, its soul, the pattern that makes this particle exactly this one and not some other. And ordinarily, that signature is a deeply private thing. You cannot even copy it. If you try to read a particle's full quantum state, the very act of looking disturbs it, smudging the thing you are trying to record. There is a rule woven into nature that forbids making a perfect copy of an unknown quantum state, ever. The signature cannot be photocopied, and yet it can be moved. Here's the gentle shape of how. Begin with two particles that are entangled, linked in that deep, distance-defying way, and place one of them far away in the hands of a distant friend. Now bring forward a third particle, the one whose signature you wish to send, and let it interact with your half of the entangled pair. You then make a careful measurement on these two together. The measurement does something curious and a little sad. It destroys the original signature entirely. The particle you wanted to send is left blank, scrubbed clean, its identity gone from where it sat. But the signature has not been lost. The measurement you made produces a small handful of ordinary information, a few simple facts, like the result of a coin flip or two. You send those facts to your distant friend the slow, normal way, by phone or by light. And when your friend receives them, they perform one last small adjustment on their half of the entangled pair, guided by what you told them. The moment they do, their particle takes on the exact signature that your particle used to have, down to the finest detail. Perfectly. The soul has crossed the distance and found a new body waiting for it. Notice what did and did not travel. No matter moved across the gap. No little speck flew from your room to your friend's. The original particle stayed exactly where it was the whole time, growing quiet and featureless as its identity drained away. What crossed the distance was the pattern alone, and even that could not arrive until your ordinary message did, carried at ordinary speed. The entangled link did part of the work in silence, but it could not finish the job on its own. Without your few words sent the slow way, your friend's particle would sit there holding nothing but noise. And so, once again, nothing here outruns light. The wonder and the rule live side by side. Scientists call this quantum teleportation, and the name is honest if you hold it lightly. It is nothing like the teleportation of stories, where a whole person dissolves in one place and reappears whole in another. Nothing is beamed, no body is dematerialized and rebuilt. What moves is something far thinner and far stranger, the pure arrangement, the recipe, the identity lifted off one particle and laid down upon another far away, while the matter itself stays home. It has been done in laboratories many times, across a room, across a city, and even between the ground and a satellite circling overhead. It is real, it works, and it carries a thought worth resting in. We tend to believe that what makes a thing itself is the stuff it is made of, this particular speck of matter, these particular atoms. But teleportation whispers a different possibility, that identity might live not in the substance at all, but in the pattern, that you could lift the whole of what a thing is away from its material, like lifting a song off the strings that played it, and set it down somewhere else entirely, and it would be the same song. The strings do not travel, the music does. There is something both unsettling and consoling in that. Unsettling because it loosens our grip on the solid stuff we trusted to make things real. Consoling because it hints that what truly defines a thing, its essence, its signature, its soul, whatever soft word you reach for, may be more portable, more enduring, less bound to any one lump of matter than we ever imagined. The original particle rests where it was left, emptied and still, asking for nothing. Far away, in a quiet room, another particle now carries everything the first one was. Its exact and perfect likeness arrived without crossing the space between. No matter made the journey. Only the pattern, only the signature, only the faint and faithful echo of what was settling gently into its new home in the dark. It can look, for all the world, as though a choice made now reaches back and rewrites what already happened. Begin with one of the oldest and loveliest experiments in physics. Send tiny particles, one at a time, toward a barrier with two narrow openings and let them land on a screen behind it. You might expect two simple stripes to build up, one behind each opening, the way thrown pebbles would pile up behind two gaps in a fence. Instead, something else appears. Over many particles, the screen fills with a pattern of many bands, light and dark and light again, the unmistakable signature of waves overlapping, as if each single particle had somehow passed through both openings at once and rippled out from each, interfering with itself on the way to the screen. Now try to catch it in the act. Place a small watcher beside the openings, just enough to tell which one each particle slips through, and the moment you can know the path, the moment that information exists anywhere in the world, the lovely banded pattern simply disappears. The particles fall into two plain stripes, like ordinary specks through ordinary gaps. It is as though the particle behaves like a spread-out wave only so long as no one can say where it went, and becomes a single definite thing the instant its path is known. That alone is strange enough to sit with for a long while. But there is a deeper turn, and this is where it begins to feel like magic. Suppose you arrange things so that the which path clue is recorded, tucked away in some second particle, some marker that carries the secret of which opening was taken. With that clue stored, the banded pattern stays gone, as expected. But now imagine you have a way to erase that clue afterward, to scramble the marker so thoroughly that the path information is truly, permanently lost, recoverable by no one. When you do this, and then sort your results in the right way, the bands come back. Erase the knowledge of the path, and the wave pattern returns from hiding. And here's the part that has launched 1,000 breathless headlines. You can wait. You can let each particle finish its journey and strike the screen, its fate apparently sealed, and only then decide whether to erase the clue or keep it. The choice comes after the particle has already arrived. And still, whether the bands appear seems to depend on a decision made when the particle was, by every ordinary reckoning, already done. It looks achingly as if the present is reaching backward to shape the past. Now let me set down the gentle truth of it, because the truth is subtler and in its own way more beautiful than the magic. Nothing actually travels backward in time. No signal is sent into the past. The particle's history is not being edited after the fact. The honest resolution lies in a quiet detail that is easy to miss. When you look at the screen as a whole, with everything jumbled together, there are no bands at all. Just a smear, a plain blur with no pattern in it. The lovely interference fringes are hidden inside that blur, and they only step forward when you sort the landing spots into groups, using the very information you gathered later about whether the clue was kept or erased. The pattern was always tangled up with that later information. You are not creating it after the fact. You are revealing a correlation that needs both halves, the early landings and the later sorting, before it can be seen at all. And because each particle on its own shows nothing special, there is no way to use any of this to send a message to yesterday. The door to the past stays firmly, gently shut. So the spookiness is real, but it is not the spookiness of time travel. It is the spookiness of a world that refuses to let which path did it take and did it ripple like a wave both be true at once. And that keeps its books so carefully that the two stories can never openly contradict each other, no matter how cleverly you try to arrange a paradox. You can delay your choice. You can scramble your clues. And every time, when all the records are finally laid side by side, the universe's account balances perfectly, with no impossible loose end. There is something steadying in that, my friend, if you let it settle over you. We so often fear that reality might be fragile, that one clever trick could break its logic and tear a hole in cause and effect. And here is a place where we pushed as hard as anyone could imagine, trying to make the future overrule the past, and the world simply smiled and kept its consistency, hiding its wholeness inside a pattern we could only see once we stopped trying to cheat. The seeming paradox lived in our storytelling, never in the particles themselves. The screen holds its quiet, jumbled glow. Somewhere in that soft blur, the bands are waiting, folded into a secret that only the full story can unfold. A pattern that was never undone and never redone, only revealed gently when at last we looked the honest way. The past stays exactly as it was, and the universe keeps its calm. The closest bonds in nature cannot be shared. We have been circling, in many ways tonight, the idea that two particles can be linked, joined so deeply that they behave as a single thing across any distance. But there is a quiet rule about these bonds that almost no one expects, and it has a name that sounds as if it belongs to poetry rather than physics. They call it the monogamy of entanglement. Here's what it means. told softly. Imagine a particle that is entangled with another as completely as it is possible to be. A perfect, total link, the strongest connection two particles can share. If that bond is as full as it can be, then this particle cannot be entangled with any third particle at all. Not a little, not faintly. Its capacity for that deep connection is wholly spent on its one partner, and there is simply nothing left over for anyone else. The bond is exclusive by the very laws of nature, not by choice and not by chance. You might wonder whether a particle could spread its connection around, linked to many partners, each a little. And in fact it can. But there is a strict budget, and the budget always balances. The more partners a particle entangles with, the weaker each of those links must become. Pour the connection into one partner and it can be total. Divide it among several and each share grows thin. There's only so much of this deep togetherness to go around. And the universe keeps careful count, never letting the sum exceed what is allowed. A particle can be everything to one, or a little to many, but never everything to more than one. This is not a soft tendency or a rough rule of thumb. It is a hard mathematical fact, proven with the same rigor as any theorem in geometry. The closer two things are bound in this deepest way, the more completely they are sealed off from the rest of the world. Total intimacy and total exclusivity turn out to be two names for the same thing. And here's where this gentle constraint becomes something quietly powerful in the world. It is precisely this rule that lets two people share an unbreakable secret. Suppose two distant friends share a pair of perfectly entangled particles and wish to use them to create a private key, a string of numbers no one else could ever know. The monogamy of entanglement is their guardian. Because if their two particles are as deeply linked as they can be, then no eavesdropper, however clever, can have quietly entangled themselves into that bond to listen in. There is no room. The connection is full. Any attempt by a third party to share in it would, by the iron arithmetic of monogamy, weaken the link between the friends. And that weakening would show itself, leaving fingerprints they could catch. The faithfulness of the bond is, quite literally, what keeps the secret safe. Let yourself feel how unusual this is among the things of the world. Most of what we know can be copied, shared, spread without limit. A song can be sung to 1,000 people and lose nothing. A piece of news can pass from mouth to mouth and grow no thinner. Knowledge, light, warmth, we are used to things that can be given away endlessly and remain whole. But this deepest of connections is not like that at all. It behaves more like devotion than like information. It cannot be given to everyone. To give it fully to one is to have none left for another. The more widely it is shared, the fainter it becomes for each. There is something almost tender in finding such a thing written into the bones of physics. We tend to think of faithfulness, of exclusive bonds, of a closeness that cannot be divided, as matters of the heart, human inventions, fragile and chosen. And here, at the smallest scale of reality, far beneath anything that could feel or choose, the universe has its own version of the same truth. The strongest connection is the one that turns away from all others. Wholeness and exclusivity are bound together. To be completely joined to one is to be sealed, gently, against the world. So tonight there's a small and quiet comfort to rest in. Somewhere, two particles are linked as fully as nature allows, and in being so linked, they have closed the door on every other partner without a sound. Their bond asks for nothing and admits no one. It is total, and because it is total, it is theirs alone. And the universe, keeping its faithful accounting, lets the door stay closed. A perfect private stillness, held between two things in the dark. Two particles that have never met, never touched, never been near each other, never shared a single moment, can still become bound together. Almost everything we say about entanglement begins with togetherness. Two particles are born from the same event, or they meet and interact, and out of that shared origin, the deep link is forged. It feels right that way. Connection, we assume, must come from contact. To be joined, two things must at some point have been together. That is how it works for us, and we quietly expect the world to follow the same rule. But the world has a quieter possibility tucked away, and it has a plain name: entanglement swapping. By it, you can take two particles that share no history whatsoever and leave them as deeply linked as any pair born together. Here's the gentle shape of how it is done. Begin with two separate pairs of entangled particles. Picture them as two pairs of friends. In the first pair, call them A and B. They are linked, born together, bound. In the second pair, C and D, likewise linked, likewise born together. Now A has never met C or D. B has never met C or D. The two pairs have lived entirely separate lives, perhaps prepared in different rooms, knowing nothing of each other. Then you do one careful thing. You bring together the two inner partners, B from the first pair and C from the second, and you make a special joint measurement on them, the kind that links their fates in that moment. And something quietly astonishing ripples outward. The act of joining B and C reaches past them to A and to D, the two particles left at the far ends, the two that never met. In that instant, A and D become entangled with each other. They are now bound in the deep, distance-defying way. These two strangers, even though no influence ever passed directly between them, even though they were never once in the same place. It is as though the connection were a kind of inheritance handed outward along the chain, or like a quiet act of matchmaking, where two people who have never spoken are introduced through a mutual friend. Except here, the introduction is so complete that the two are left as bonded as if they had been together all along. The link did not require their meeting. It only required that each be linked to a partner, and that those partners then be joined. And let yourself notice what this means. The two outer particles end up sharing the deepest connection nature offers, yet they have no common past at all. There is no shared birth, no moment of contact, no history between them to point to and say, here's where their bond began. The bond simply exists, conjured into being by an event that happened to their partners, somewhere off to the side. Connection, it turns out, does not always need contact. It can be passed, inherited, woven between things that were strangers a moment before. This is no mere curiosity either. It is one of the great hopes of those who dream of carrying entanglement across the whole face of the earth. The deep links between particles are fragile, and they fade over long distances, the way a faint signal dwindles down a long wire. But with swapping, you need not stretch a single bond across the whole gulf. You can lay down a chain of shorter links, pair after pair, like stepping stones, and then join the inner partners one after another, passing the connection along, until two particles at opposite ends of a continent find themselves entangled, having never come within 1,000 miles of each other. It is the quiet trick that might one day stitch a network of quantum connections across the world. There is something that stirs the heart in this if you follow it down. We carry, most of us, a deep assumption that closeness must be earned through shared time, that to be truly bound to someone, you must have been with them, built a history, gathered a past together. And here is nature, at its smallest scale, gently suggesting otherwise. That a bond can arise between two things with nothing in common, no shared yesterday, no moment of meeting, bound not by their own history, but by the connections each already carried. As if relationship were less a thing you build from scratch, and more a thing that can be passed along, kindled at a distance, inherited from the links that came before. So tonight there is a soft and surprising thing to rest in. Somewhere, two particles that have never met now share the deepest closeness the universe allows. Strangers made kin by a quiet event between their partners. Bound across a distance they never crossed. They ask nothing and explain nothing. They simply rest there, joined, two lives that never touched and yet are one, holding their improbable bond in the dark. For 50 years, some of the most careful people who ever lived tried to prove the spookiness was just a trick, and reality turned them down gently every single time. The story begins with a test. Once it was understood that two distant particles agree more often than any secret prearrangement could allow, there was, in principle, a way to check it in a laboratory. And when the checks were first run, decades ago, the particles behaved exactly as the strange quantum predictions said they should. The agreement was too strong. The comfortable explanation that the particles were merely reading from identical notes prepared in advance seemed to fail. But science is rightly stubborn, and a single experiment is never quite enough. Skeptics, doing their proper work, kept asking, "Are you truly sure? Might there be some ordinary loophole, some quiet trapdoor through which a perfectly normal explanation could still slip?" And for a long time, the honest answer was yes, there might be. There were a few such trapdoors, and each one had to be hunted down and closed. One was about the particles you miss. The delicate detectors of the early days caught only a fraction of the particles sent their way. Many slipped through unseen, and a doubter could argue fairly that perhaps the ones you happened to catch were a biased sample, that if only you could see them all, the spooky pattern might melt away, and the homely explanation might be saved. To close this trapdoor, physicists needed detectors so efficient that hardly any particle escaped uncounted. Another trapdoor was about distance and time and the chance of a whisper. When you measure one particle here and its partner there, you must be certain that no ordinary signal could have passed between the two measuring stations to coordinate the results. No message, even one traveling at the speed of light, sneaking from one side to the other to arrange the agreement. If the two stations were too close, or the measurements too slow, there was always time for such a whisper, and the spookiness might be no more than careful timing. To close this trapdoor, the two stations had to be set far apart, and each measurement made and finished so swiftly that not even light could carry word from one to the other in time to matter. And there was a subtler trapdoor still, about the choices themselves. The whole test depends on each station freely choosing, at the last possible instant, which question to ask its particle. But what if those choices were not truly free? What if some hidden thread connected the choice makers to the particles, quietly steering both? To close this trapdoor, The choices had to be made by something as unpredictable as the universe allows, and made so late that nothing could have known them in advance. For decade after decade, physicists chased these trapdoors. They built better detectors that missed fewer particles. They moved their stations farther apart and made their measurements faster, racing light itself. They found ever purer sources of randomness to make their choices. Each experiment closed one trapdoor or perhaps two, but for a long, long time, no single experiment could close them all at once. And as long as even one stood open, a sliver of hope remained for the ordinary, unspooky world. Somewhere in that gap, the comfortable explanation might still be hiding. Then, in a single remarkable year, the gap finally closed. Working in different places with different methods, some using particles of light, some using the spins of single electrons held in tiny flaws inside diamonds, stretched apart across more than a kilometer. Several teams at last performed the test with every major trapdoor shut at the same time. No biased sample, no room for a whisper, no tampered choices. The escape routes were all sealed together, and the answer came back unchanged, clear, and final. The particles agree more often than any secret plan could ever allow. There is no ordinary explanation hiding in the shadows. The spookiness is simply real. Years later, the makers of these long and patient experiments were given the Nobel Prize, a quiet acknowledgement that the question had been settled as firmly as such things can ever be settled, after half a century of the most careful doubting imaginable. Let yourself rest in what that half-century really was. It was not a story of people rushing to believe something strange. It was the opposite. It was the story of a whole community of careful minds doing everything in their power to find a way out, to show that the world was ordinary after all, that the connection was a trick of missed particles or sneaking signals or rigged choices. They tried with all their ingenuity for 50 years to make the weirdness disappear, and the universe with infinite patience declined. Every trapdoor they opened led only back to the same impossible truth. There is something deeply moving in that kind of honesty, in a search whose whole purpose was to disprove the wonder, and which ended by confirming it beyond reasonable doubt. The spookiness was not wished into being by dreamers. It was forced upon the doubters by the world itself. And so the particles go on, far apart, agreeing perfectly, holding a connection that 50 years of the finest skepticism could not explain away. The trapdoors are all closed now. The hunt is over, and what remains settled at last in the quiet is simply the strange and steady fact: the bond is real, and the universe was telling the truth all along. Your bedroom is stubbornly, reliably singular, and that, it turns out, is the strange part. We have wandered tonight through a world where the smallest things hold many possibilities at once, where a particle can be a blur of maybes until someone looks, and a fair question hangs over all of it, gentle but insistent. If that is how the small world truly is, then why is the world around you so utterly definite? Why is your chair simply there, in one place, one shape, one solid certainty? Why have you never once walked into a room and found it shimmering between two arrangements, or caught a teacup being in two spots at the same time? If the threads of reality are woven from blurry, undecided stuff, why is the cloth they make so clear and so still? The answer is one of the quiet triumphs of modern physics, and it has a soft name: decoherence. And the heart of it is this: nothing in your room is ever truly alone. Picture any ordinary object. A coin on your dresser, say. We imagine it sitting there in perfect isolation, but it is nothing of the kind. It is being touched constantly and from every side by the world around it. Particles of light rain down on it and scatter away. Molecules of air drift against it and bounce off. Faint warmth radiates from it into the room. And here is the crucial thing. Each of these tiny touches carries away a little whisper of information about the coin. Where it is, how it sits, which way it faces. The coin cannot help but leave its mark on everything that brushes against it. The way a person moving through a dark room cannot help but stir the air and warm the space they pass through. Now suppose the coin tried to hold itself in a quantum blur, to be in two states at once, the way a lone particle can. The blur would not simply vanish. Instead, it would begin to leak. Each particle of light, each molecule of air that touched the coin would carry off a fragment of that blur into the surrounding world, until the delicate quantum togetherness was no longer held within the coin at all, but smeared out across countless particles in the room, the air, the walls, drifting away in every direction. And once it is spread that thin, scattered across uncountable specks of the environment, hopelessly mingled, impossible ever to gather back together, the blur can no longer show itself. The coin looks, to anyone who could ever observe it, like one definite thing in one definite place. The weirdness is not destroyed. It is diluted beyond all recovery, poured out into the world until no trace of it can be found in the coin itself. This is what it means to say the environment is always endlessly measuring, not with eyes or instruments, but simply by touching, by the ceaseless brush of light and air and warmth that no object can escape. Every contact is a kind of looking, and the world is looking at everything all the time. And this is why size matters so much. A single particle, well shielded and left alone, can hold its blurry quantum state for a long while because so little touches it. But a coin, a teacup, a chair, these are vast cities of particles, touched by the world a staggering number of times every instant. For them, the leaking happens almost unimaginably fast, so fast that the quantum blur is gone before any blink could catch it. This is why you have never seen a large thing in two states at once. The bigger it is, the more the world is touching it, and the more swiftly its weirdness drains away into the surroundings. The strangeness is real for the chair too. It is simply hidden, instantly and completely, the moment the chair meets the world. It is worth saying, gently and honestly, what decoherence does and does not settle. It explains beautifully why the everyday world looks so definite, why we are never confronted with shimmering, half-here objects. But there remains a deeper question it does not fully answer. Why, out of all the possibilities, we end up seeing one particular outcome rather than another? That last step, the selection of a single fact from the spread of maybes, is still debated by careful thinkers, and tangled up with the deepest unsolved puzzles of the theory. So decoherence does not make the mystery disappear. What it does is show us where the mystery has been hiding all along, not in some far-off laboratory, but woven invisibly into every ordinary moment, smeared into the very air of the room you are resting in. Let that thought settle over you softly. The solid, singular world you trust, the firm floor, the still walls, the dependable shape of everything around you, is not solid because the strangeness is absent. It is solid because the strangeness has been spread so thin, so fast, by the gentle, endless touch of the world, that you could never hope to see it. The quantum blur is not somewhere else. It is here, in this room, leaking out of every object into the air, the way warmth leaves a sleeping body into the cool of the night. There is no wall between the quantum world and yours. Only a fog, a soft, constant fog of the world touching itself everywhere at once, turning blur into certainty quietly enough that you never notice it happen. The chair stays where it is. The room stays still. And all around you, unseen and unfelt, the strangeness goes on dissolving into the dark, leaving behind only the calm, singular world that holds you now. There is an experiment that can overturn an entire way of seeing the world in a single try. Usually, proving that nature is strange takes patience. You set up a delicate test, run it thousands upon thousands of times, and slowly watch the tally build, until the numbers settle just past the line that any ordinary common sense explanation could allow. It is a victory won grain by grain, the way water wears down stone. For a long time, this was the only way we had to show that the deep connection between distant particles could not be some hidden, sensible mechanism in disguise. You needed mountains of data, and even then, the result was a matter of degree, the particles agreeing a little more often than they had any right to. Think of how you would catch a weighted coin. You cannot tell from a single toss. A fair coin can come up heads once easily enough. You have to flip it again and again, watching the heads pile up until the imbalance is too large to be chance. That is proof by accumulation, and it is how the strangeness of entanglement was first pinned down. But imagine instead that you saw a coin land balanced on its edge, and then do it again and again, every single time you threw it. Something no ordinary coin could ever do even once. You would not need a tally. A single impossible landing would tell you everything. The world had broken a rule you thought unbreakable. There is a version of the quantum story exactly like that, and it comes from linking not two particles, but three. Three particles can be prepared together in a special shared state, a particular kind of threefold entanglement, named for the three physicists who first worked out what it could do. It binds three separate things into a single quantum whole. And with three particles joined this way, you no longer need thousands of runs and a careful count. A single perfect set of measurements, performed just once, can give an answer that the ordinary picture of reality calls not merely unlikely, but flatly impossible. Let me show you the shape of it gently. Picture the three particles carried far apart, one to each of three distant rooms. In the comfortable old picture, each particle already holds its answers, fixed and waiting, decided long before anyone arrives to look. If that were so, then when the three rooms each make their measurement, and you bring the three results together and combine them in a certain way, the outcome would have to be one definite thing, a result you could work out in advance with nothing more than honest arithmetic. The common sense picture does not hedge. It commits firmly to a single answer. And quantum mechanics predicts the exact opposite answer, and predicts it with complete certainty. Every single time you perform the measurement, three entangled particles give precisely the result that the common sense picture swears can never occur. So one clean run is enough. A single set of measurements where the particles behave as quantum theory says they will. And the old picture, the one in which everything quietly carries its properties in advance, is simply finished. There is no room left for it, no escape into Perhaps it averages out over time, because the very first trial already lands on the forbidden outcome. Where the older proof was a slow erosion, this one is a single decisive stroke, like that impossible coin balanced on its edge. Sit with how unusual that is. We are used to the idea that overturning a deep belief about the world takes overwhelming evidence, gathered patiently across years, weighed and reweighed by careful people. And here is a corner of reality where, in principle, one experiment done a single time can topple an entire way of imagining how things are. The contradiction is not a faint statistical tilt coaxed out of the numbers. It is logical, stark, and absolute. As sharp as discovering that something you were certain was true simply cannot be. There is something almost dizzying in that, if you let it wash over you. A worldview undone not by slow accumulation, but in a single moment. It suggests that the strangeness at the heart of matter is not some subtle bias hiding in the statistics, but something woven so deeply into reality that it can stand up and announce itself, fully and at once in a single breath. The universe does not whisper this particular secret. When you ask it the right way, it says it plainly, all at once, leaving no room to doubt. The three particles do not know what they have done. They rest wherever they have been carried, far apart in their separate rooms, holding among them a shared answer that no tale of pre-written fates could ever account for. And in a single look, one measurement made just once, an entire way of picturing the world, comfortable and ancient and deeply human, loosens its grip and drifts quietly away into the dark. There is a kind of secret that announces the very moment anyone tries to steal it. Think first about how fragile ordinary secrets are. A letter can be steamed open, read, photographed, sealed again, and slipped back into the post, and you would never know it had been touched. A message sent across the world can be copied silently somewhere along the way, the copy carried off while the original sails on, innocent and unaware. This is the quiet vulnerability beneath almost everything we try to keep private. Information in the ordinary world can be copied without leaving a mark. The thief takes a perfect duplicate, and the owner notices nothing missing because nothing is missing. The secret simply now belongs to two people instead of one. A secret written in the quantum world cannot be stolen that way. The reason reaches down into the deepest rules of how small things behave. There is a law woven into nature that forbids making a perfect copy of an unknown quantum state. You cannot duplicate it, cannot photograph it, cannot quietly clone it and send the original on its way. And more than that, the very act of trying to read such a state disturbs it, leaving it changed, smudged, no longer quite what it was. To look is to touch, to measure is to disturb. The quantum world does not let you observe it in secret. So imagine two distant friends who wish to share a secret key, a long string of numbers that only the two of them will ever know, with which they can lock their messages safely away. Instead of sending those numbers in ordinary form, they encode them in the delicate quantum states of individual particles, sent one at a time across the distance. Now suppose a spy lies in wait along the path, hoping to read each particle and learn the key. The spy cannot do it silently. Every particle the spy intercepts and measures is disturbed by the measuring, knocked subtly out of its original state. And when the two friends later compare a small sample of their particles, checking, openly, whether the results still match the way they should, those disturbances show themselves as errors, a a scattering of mismatches that should not be there. The fingerprints of the intruder are written into the particles themselves. The friends see the tampering, throw that key away unused, and quietly begin again. The spy comes away with nothing but a handful of damaged particles and no secret at all. There is an even more beautiful version of this, built directly on entanglement. Suppose the two friends share pairs of deeply entangled particles, one half held by each. They can run a small test of the connection between their halves, checking that the bond between them is intact, as strong and unbroken as the laws of physics allow. If no one has interfered, the connection passes the test, and they know their key is theirs alone. But if a spy has meddled, has tried to slip into the link and listen, the very act of intrusion weakens the bond, and the test reveals it. The faithfulness of the entanglement stands guard over the secret. A broken connection is a confession. Let yourself feel how different this is from every lock we usually trust. Almost all our secrecy rests on locks that are merely hard to pick, scrambled with a mathematical puzzle so difficult that no ordinary effort could solve it in a lifetime. But hard is not the same as impossible. A cleverer method or a powerful enough machine might one day crack such a puzzle, and then every secret it ever guarded would lie open at once, perhaps without anyone even knowing it had happened. The security was always borrowed against the future. Here, the protection is of an entirely different kind. It does not rest on difficulty. It rests on the laws of the universe themselves, on the simple, unbendable fact that you cannot look at a quantum thing without changing it. The intrusion is not merely hard to hide. It is physically impossible to hide. This is not a daydream either. It has been done. Secret keys shared this way across cities, down long threads of glass, and even between the ground and a satellite passing far overhead, listening for the faint arrival of single particles of light. The quiet rules of the small world turned into a vault that no spy can enter unseen. There is something deeply consoling in that, if you follow it down. We live so much of our lives trusting locks that might, in principle, be broken, hoping the thief is not clever enough, not patient enough, not yet equipped with the right tool. And here, written into the bones of reality, is a promise of a different sort. A place where privacy is not a gamble, but a guarantee, where the universe itself refuses to let a secret be quietly taken. Two friends, far apart, share a string of numbers that belongs to them alone. No one else can ever read it without leaving a trace, and so no one else will ever read it at all. The key rests between them, perfectly private, watched over by nothing more than the quiet, unbreakable rules of the world. A small, safe stillness held across the distance in the dark. Somewhere, a machine is solving a problem by letting its wrong answers cancel each other out, the way ripples meeting on a pond can flatten into stillness. To feel how strange that is, picture first how an ordinary computer thinks. Underneath everything it does are tiny switches, each one firmly on or off, a 1 or a 0, definite and certain at every instant. To work through a hard problem, it tries possibilities in turn, or splits the labor among many switches working side by side, but always with each switch committed to a single solid value. It is a vast, fast, tireless accountant, checking one thing after another, never holding two answers in the same place at the same time. A quantum computer is built from something far stranger. Its switches, its quantum bits, need not be firmly on or off. Each one can hover in a blend of on and off together, a soft mixture of both at once. And more remarkable still, these bits can be entangled with one another, linked so deeply that the whole machine holds connections and correlations no ordinary computer could ever cheaply capture. The state of the machine is not a list of definite ones and zeros, but a single woven whole, all its parts bound together in ways that have no everyday picture. Here it is tempting to say that such a machine simply tries every possible answer at the same time, and you will often hear it described that way. But that picture, lovely as it sounds, is misleading, and the truth is stranger and more beautiful. The real magic is more like waves than like a frantic search. Each possible answer to the problem is given something like a wave of its own, and the machine is carefully arranged so that all these waves interfere with one another. Crest meeting trough, peak meeting hollow. The waves that lead to wrong answers are made to cancel out, fading toward nothing as they overlap and cancel, the way two ripples can meet and leave flat water behind. And the waves that lead to the right answer are made to reinforce, to swell and gather strength, rising higher and higher, so that when you finally look at the machine and ask it for its answer, that one answer is overwhelmingly the thing you find. Entanglement is the deep connection among the parts that makes this delicate orchestration possible at all. It is what lets the waves be woven together tightly enough to interfere in just the right way. So a quantum computer is not really a machine that checks everything at once. It is a machine that arranges a vast and intricate interference of possibilities, and then lets the answer rise up out of the pattern. Like a single clear tone emerging from a sea of noise as all the wrong notes quietly cancel. It is worth saying honestly what such a machine can and cannot do. It is not simply a faster computer for everything. For most ordinary tasks, it offers no advantage at all. Its strange gifts apply only to certain special problems, finding the hidden factors of enormous numbers, searching through vast unsorted spaces, and above all, simulating the behavior of other quantum things, like the dance of atoms inside a molecule, which ordinary computers struggle to capture. And building these machines is extraordinarily hard, because the delicate quantum states they depend on are so terribly fragile. The faintest touch from the outside world, a stray particle of heat, a whisper of light, disturbs the careful interference, and the whole pattern collapses into ordinary noise. This is why today's quantum computers are still small and finicky things, kept colder than the depths of space, shielded with great care from every passing disturbance. The principle is sound and proven. The building of large, steady machines is a labor still very much underway. Let yourself rest in the deep irony of it. The connection between quantum things can seem so spooky and so useless, a link so strange that it cannot even be used to send a message across a room. And yet that very same ghostly property, the deep entanglement of quantum things, turns out to be the engine of an entirely new kind of computation, a power our ordinary machines can never match. The most mysterious feature of the small world, the one that most offended common sense, becomes a tool of real and practical might. The strangeness was not a flaw to be explained away. It was a resource, waiting all along to be used. There is something quietly wondrous in that pattern. How often the things that seem most useless, most baffling, most resistant to sense, turn out to hold a hidden usefulness we discover only by following the mystery patiently to its end. The machine sits in its cold and silent chamber, shielded from every stray whisper of the world, holding its woven web of possibilities. Inside it, unseen, countless answers rise and fall like waves on a darkened sea. The wrong ones fading into stillness, the right one gathering quietly toward the surface. And when at last someone looks, there it is. A single answer, left standing alone in the quiet, lifted out of the depths by nothing more than the gentle cancellation of everything it was not. Two tiny drums, each one far smaller than a grain of sand, have been made to tremble in time with a single shared quantum heartbeat. We tend to imagine that entanglement belongs entirely to the realm of the unimaginably small, to lone particles, single atoms, flecks of light too tiny to picture. It feels like a delicate magic that could only happen down there, far beneath anything we could see or touch, in a world so small it hardly seems real. The deep strangeness, we assume, must surely fade away as things grow larger, dissolving long before it reaches the scale of anything we could hold in a hand. But the boundary keeps moving, and no one has yet found where it stops. Physicists have taken two minuscule drums, tiny membranes of metal, each one a vibrating surface smaller than a grain of sand, and yet each built from many trillions of atoms, and linked them in that deep quantum way so that their tremblings share a single state. Stir a motion in one and the other answers, the two of them bound into one quantum whole, though nothing ordinary passes between them. These are not single particles. They are objects, manufactured things, vast cities of atoms, and still they were made to hold the spooky connection between them. They have gone further. Physicists have entangled small diamonds, real gems large enough to see with the naked eye, set a short distance apart on a tabletop. For the briefest flicker of time, a sliver of an instant almost too short to name, the two diamonds were bound together through a single shared vibration humming through them both, linked so that they were, for that moment, one quantum system rather than two separate stones. Two things you could have pointed to and picked up, joined by the same connection we thought belonged only to the world of the invisibly small. And further still, physicists have entangled great clouds of atoms, billions upon billions of them at once, vast gatherings of matter bound into a single shared quantum state. Not one atom, not a mere handful, but multitudes, held together in that deep connection, all of them sharing one fate. Let yourself sit with what this quietly overturns. We had assumed, without quite saying it aloud, that there must be a size at which the strangeness has to stop. Some line beyond which a thing becomes too big, too warm, too solid, too real to behave in such ghostly ways. It seemed only sensible. The quantum world was for the tiny, the ordinary world for everything we could see. But the experiments keep pushing that supposed line outward, past single particles, past atoms, to drums and diamonds and clouds on the very edge of the visible, and at no point have they struck a wall. The strangeness does not seem to know it is supposed to stop. Why then do the large things around you, your chair, your hand, the lamp beside the bed, never shimmer with quantum weirdness? The answer seems to be not that they cannot, but that the world will not leave them alone long enough to show it. A large object is touched ceaselessly by its surroundings, by light, by warmth, by the endless brush of the air. And each touch is a kind of looking that smears the delicate connection away, almost the instant it could form. The drums and the diamonds revealed their secret only because they were shielded with extraordinary care, cooled and isolated and kept from the touch of the watching world. Protect a thing well enough from being touched, and its quantum nature lingers at scales that ought to astonish us. The weirdness was never a property only of the small. It was a property of the undisturbed. There is something that stirs the imagination in that, if you let it. It hints that there may be no true ceiling on this strangeness at all. That the line between the quantum and the everyday is not a hard edge written into nature, but a soft and movable thing, set only by how completely we can shield a thing from the world's relentless gaze. In principle, the deep connection might reach all the way up to objects we could cradle in our palms. If only we could keep them perfectly, impossibly still and untouched. The smallness was never the point. The solitude was. The tiny drum rests in its cold and silent chamber, trembling faintly in time with a twin it has no ordinary way to feel, no wire between them, no signal passing, only the shared quantum motion that binds them into one. Two small things on the very edge of sight, each built from trillions of atoms that holding a single quiet heartbeat between them in the dark. There is a daring idea that the invisible thread between two entangled particles might be a tiny tunnel through space itself. I want to be honest with you from the very first breath of this one. What I am about to describe is a conjecture, not a settled fact. It is a frontier idea, dreamed up by theorists reaching toward the deepest questions in physics, and no experiment has been able to test it. Hold it lightly, the way you would hold a beautiful possibility rather than a proven truth. But it is one of the most astonishing thoughts in all of modern science, and it is worth wandering through slowly in the dark. It begins by bringing together two ideas that, at first, seem to have nothing to do with each other. The first is the deep connection of entanglement, two particles linked so completely that they behave as one across any distance. The spooky bond we cannot fully explain. The second comes from the equations of gravity, from our best understanding of how space and time can bend and curve. Hidden in those equations is the possibility of a wormhole, a tunnel through the very fabric of space, a shortcut that could in principle join two far apart places directly, like folding a sheet of paper so that two distant points touch. Wormholes have lived in the mathematics of gravity for a long time, strange and theoretical, mostly regarded as curiosities. And here's the conjecture, the daring leap, that these two things, the spooky entanglement link between particles and the geometric tunnel through space, might be one and the same thing, seen from two different sides. That every entangled pair is joined in some hidden way by its own microscopic wormhole. The thread we cannot see when two particles are linked across a distance would not be a metaphor at all, but a real, tiny tunnel through the deeper structure of space, far too small and too strange ever to crawl through, yet genuinely there, binding the pair together beneath the surface of things. Let that settle for a moment, gently, before we go further. Two of the most mysterious ideas in all of physics, the ghostly connection of entanglement and the warping of space into tunnels and shortcuts, quietly folded into a single mystery. The spooky link and the bent space revealed as two faces of one thing. And there is a deeper, dizzier thought folded inside this one, and it too is unproven, a frontier dream still being explored. If entanglement and the geometry of space are this intimately related, then perhaps the smooth space between all things, the very stage on which the entire universe unfolds, The emptiness through which light travels and worlds turn might itself be woven out of countless entangled threads. There is theoretical work, careful and serious though far from confirmed, suggesting that if you could somehow imagine unpicking the entanglement between two neighboring regions of space, those regions would drift apart, the distance between them stretching and tearing until the space itself came undone, as though distance were held together, stitched into being by entanglement underneath. In this dream, geometry is not the foundation everything rests upon. It is something that rises up out of a deeper layer, out of connection itself. I will say it once more because it matters. None of this is proven. There is no experiment yet that can reach down and check it. It lives for now in the realm of mathematics and imagination, a possibility that a handful of the world's deepest thinkers find beautiful enough and suggestive enough to pursue. It may turn out to be true in some form. It may turn out to be only a lovely mistake. We do not yet know, but even held as a dream, sit with what it whispers. It suggests that separation itself, the distance between you and a far-off star, the gulf between two particles, the empty space that seems to hold everything apart, might be a kind of surface appearance, woven from threads of togetherness running underneath. That what looks like apartness might be made, at the deepest level, from connection. That the universe might be far more bound to itself than its vast and lonely distances ever let on. There is a strange comfort in even imagining such a thing. We move through a world that feels so often defined by separation, by the spaces between us, the distances we cannot cross, the loneliness of a cosmos so unthinkably large. And here's a thought, unproven and luminous, that turns the picture quietly inside out. Perhaps distance is not the deepest truth, but the surface of something woven whole. Two entangled particles rest far apart, joined by a connection we cannot see. And perhaps, if this dream holds any truth, by a tunnel too small and too strange to ever find, a thread that may be made of the very same stuff as the space stretched out between them. We do not know, we may never know. But the thought drifts there in the dark, soft and vast and unresolved. A quiet possibility that the universe, beneath all its distances, might be holding hands with itself. There is a serious idea in physics that says the particle never really chooses, and that perhaps neither do you. Let me be clear from the outset, gently, this is an interpretation, one way among several of making sense of the quantum world, and it is not a proven fact. Thoughtful physicists hold it, other thoughtful physicists doubt it. It is offered here not as settled truth, but as one of the most mind-stretching possibilities ever taken seriously by careful people. Hold it lightly and let it open the night a little wider. It begins with the old, deep puzzle we keep circling, that a particle, before it is looked at, hovers in many possibilities at once, a soft blur of maybes, and then, the instant it is measured, seems to snap to a single definite outcome, all the other possibilities vanishing as though they never were. This sudden snapping has troubled physicists for a century. Where do the other possibilities go? What makes the world choose? And this idea answers the puzzle in the most radical way imaginable. It says there is no snapping at all. Nothing ever collapses. The world never truly chooses. Instead, in this picture, when a measurement happens, every possibility remains entirely real, and the world itself quietly divides. The particle, the instrument that measures it, the room, the observer, the whole surrounding world all split into branches. one branch for each possible outcome. And each branch is just as real as every other. In one branch, the particle was found spinning upward, and in that branch there is a version of you who saw up and remembers seeing it. In another branch, the particle was found spinning downward, and there's a version of you who saw down. Equally real, equally certain of what they witnessed. Neither branch is the true one. Neither outcome is the real result, while the other is a phantom. They simply both happen, each in its own branch, each carrying its own copy of you, going on unaware of the other. The single outcome you remember seeing tonight, whatever it was, is in this view merely the one that belongs to the branch you happen to find yourself in. The other outcomes are not gone. They are only elsewhere, in branches you can no longer reach or feel, each as solid and as lived in as your own. This is the idea sometimes called many worlds. First set down decades ago by a young physicist puzzling over what the equations might be saying if we simply took them at their word, without adding any mysterious collapse by hand. And in this picture, the universe is endlessly, ceaselessly branching, dividing into uncountable parallel versions of itself every time anything is measured, every time a quantum question is answered. Which is to say, constantly everywhere, in every corner of reality, a silent and unstoppable blossoming of worlds. I must say plainly what makes this so strange to weigh. By its very design, this idea predicts exactly the same things you would observe as ordinary quantum mechanics. The same probabilities, the same results in every experiment. The other branches, if they exist, are forever beyond our reach. We can never see them, never visit them, never receive so much as a whisper from them. And so no experiment we know how to perform can confirm this picture or rule it out. It may be the literal truth of how reality works. It may be a beautiful overreading of the mathematics. For now, it sits beyond the reach of our testing. A possibility we can reason about, but cannot yet weigh on any scale. And yet, let yourself drift for a moment into what it would mean if it were so. It would mean that every road not taken was in fact taken by someone who is also you. Every choice you agonized over, every chance that fell one way and might have fallen another, every quantum flicker that could have gone differently, all of them happened, each in its own branch, each real. The world would not be a single thread of events winding through time, but an endlessly branching tree, vast beyond all imagining, every possible version of every moment somewhere alive. Whether or not it is true, there is something that stills the mind in even considering it. We carry, most of us, a quiet ache over the lives we did not live, the turns we did not take, the selves we might have been. And here's a thought, unproven, untestable, perhaps forever beyond our knowing, that whispers those other selves might not be lost at all, only elsewhere, living out the paths we set down, in worlds branching softly away from our own. So here is a gentle thing to carry towards sleep, held as the dream it is. If this idea holds any truth, then somewhere, every outcome that could have happened tonight is happening. Every way this quiet evening might unfold is unfolding, in its own branch of a ceaselessly dividing world. And in each of them, perhaps, there is a version of you, settling into the dark, letting the day go, drifting toward rest, a thought far too large to truly hold. Let it be vast and unresolved, and let it carry you gently down into whichever branch is yours tonight. Two people can stand on either side of a door and disagree, honestly and correctly, about whether anything has actually happened. Imagine a scientist working inside a laboratory, and imagine that this laboratory is sealed so perfectly, so completely, that nothing within it can leak out to the world beyond. No sound escaping, no glimmer of light, not the faintest trace of warmth or vibration slipping past its walls. From the outside, the lab is a perfect silent box, utterly cut off. Inside, the scientist goes about her work. She takes a single quantum particle, one of those tiny things that hovers in a blur of possibilities until it is measured, and she measures it, and she sees a definite result. The particle was spinning upward, let us say. To her, there is no ambiguity at all. Something happened. A fact came into being. She writes it down in her notebook. Up. For her, the matter is closed. Now imagine a colleague standing outside that sealed laboratory. Someone who takes the rules of quantum mechanics very seriously and applies them not just to tiny particles but to everything consistently, all the way up. From where he stands, no information has escaped the sealed box. Nothing inside has touched the world outside. And so, following the rules faithfully, he must describe the entire laboratory, the particle, the instruments, and the scientist herself, as a single quantum system still hovering in a blur of possibilities. In his description, no definite outcome has happened yet. The scientist inside is, from his point of view, in a strange blended state of having seen up and having seen down at once, the whole sealed lab a soft cloud of undecided maybes, waiting. So now there are two descriptions of the very same moment, and both of them follow the rules correctly. The scientist inside is certain. A definite thing has happened. The answer is up. The matter is settled. The colleague outside is equally entitled to say that nothing definite has happened yet, that the lab and everyone in it remain an unresolved blur. Both are using quantum mechanics exactly as it is meant to be used, and they flatly disagree about whether a real definite event has taken place at all. Which one is right? Did something happen inside that room, or did it not? This puzzle is far more than a clever riddle, and careful thinkers have sharpened it in recent years into something genuinely unsettling. By extending the scenario, adding more sealed observers, more layers, more steps, they have shown that a small handful of perfectly reasonable assumptions, the kind we would all be deeply reluctant to give up, cannot all be true at the same time. There is the assumption that there is a single, shared set of facts about the world, that what happened, happened, the same for everyone, and any two observers who reason correctly must ultimately agree. There is the assumption that quantum mechanics applies to observers themselves, to scientists in sealed rooms, and not only to the smallest particles. And there is the assumption that an experimenter is free to choose what they will measure. Each of these feels almost too obvious to question, and yet, held all together, they appear to lead to a contradiction, a knot that cannot be untied while keeping every strand. At least one of these cherished beliefs, it seems, must quietly bend. Let me be careful here, because this is not a proven verdict that reality is merely a matter of opinion, or that nothing is truly real until someone decides it is. It is subtler and more honest than that. What this puzzle shows is that some of our most basic, most comfortable assumptions about the world cannot all stand together once quantum mechanics is taken fully seriously and applied to observers as well as to particles. And physicists do not agree on which assumption to let go. It is a living question, explored in careful arguments and even in small, delicate experiments that stand in for the sealed lab and its watcher. The disagreement is real, and the resolution is not yet known. But sit with what it presses upon. It touches the most basic thing most of us believe without ever examining it, that there is one shared world, one single set of facts, the same for everyone, whether or not anyone happens to be looking. The mountain was there before the climber. The fallen tree made its sound in the empty forest. What is real for all, independent of any observer. This is the bedrock beneath nearly everything we think. And here's a puzzle, drawn straight from our best theory of the small, gently suggesting that this bedrock might not be as solid as it feels. That what really happened might, in some strange way, depend on where you are standing. It is among the most disorienting thoughts in all of physics, and no one can yet tell you how it resolves. A sealed room rests in the quiet. Inside it, a scientist has written a single word in her notebook, certain of what she saw. Outside it, a colleague describes that same room as a cloud of undecided possibility, equally certain that nothing has yet been settled. Both descriptions are true, somehow, at once. Two faithful accounts of one moment that refuse to agree. And the question of whether the world is a single shared story or something stranger and more divided rests there gently between them, unanswered in the dark. A small bird may find its way across the whole face of the earth by seeing the planet's magnetic field with its own eyes. Each autumn, certain songbirds set out on journeys almost too vast to believe. The European robin among them, a creature small enough to hold in a cupped hand, will travel hundreds or even thousands of miles, leaving one land for another as the seasons turn, and somehow it knows which way to go. For a long time, how such a bird finds its direction was a deep and genuine mystery. It has no map, no instrument, no one to follow. And yet, night after night, it turns unerringly toward its distant destination, as though it could feel the very shape of the world around it. The leading explanation now is astonishing, and I want to walk through it with the care it deserves, because parts of it are well supported and parts of it are still debated. The idea is that the bird may, in a real sense, see the Earth's magnetic field, that delicate, invisible field that threads through the whole planet, the one we ourselves can only detect with a compass. And it may see it through a quiet bit of quantum physics happening inside its own eye. Here's how the picture goes. In the cells of the bird's retina, there is a special light-sensitive protein. When a particle of light strikes this protein, it can knock loose a pair of electrons, and these two electrons, though they may drift slightly apart within the molecule, remain linked, their tiny magnetic properties, their spins, bound together and possibly entangled in that deep quantum way. Now, the spins of these linked electrons are exquisitely sensitive to any magnetic field around them, even one as faint as the Earth's. And the chemical reaction that follows, what the pair of electrons goes on to do, depends delicately on how their linked spins are oriented relative to that field. So as the bird turns its head, shifting the angle between its eye and the planet's magnetic field, the balance of the reaction shifts with it. And this, the idea suggests, may paint a faint pattern across the bird's vision, a soft smudge of light or shadow that changes as it turns, a living compass drawn directly onto what the bird sees, conjured out of quantum mechanics in the warm darkness of its eye. Let me be honest about where the certainty ends, that birds navigate using a light-dependent process in the eye that is sensitive to magnetic fields. This has real experimental support, and it is the leading explanation among scientists who study it. But the finer quantum details, and especially the precise role of entanglement and how long that delicate linked state could possibly survive inside a living cell, remain matters of active debate. It is a strong and beautiful hypothesis, supported by genuine evidence and still not fully proven. We are watching scientists work it out in real time. And there is a second place where life may have brushed against the quantum world, though here the ground is even more contested. When plants and certain bacteria capture sunlight, gathering its energy to build the sugars that feed nearly all life on Earth, that captured energy must travel through a forest of molecules to reach the place where it can be put to use. Some experiments have hinted that this energy may, for the briefest moments, move not like a simple hopping packet, but like a wave exploring many paths at once. A kind of quantum coherence that might let it find its way with remarkable efficiency. But whether this effect is truly quantum, whether it lasts long enough to matter, and whether it actually plays a useful role in the warm, wet, jostling environment of a living cell, all of this is still genuinely argued over among scientists. It is a tantalizing possibility, not a settled fact. Still, let yourself sit with the wonder of even the possibility. It raises a question that can stop the mind. Did life, blindly, patiently, across countless millions of years, stumble upon and learn to use the spookiest and most delicate trick in all of physics, long, long before any human being understood it or even imagined it existed? If even part of this turns out to be true, it would mean that quantum mechanics is not merely the business of cold laboratories and carefully shielded machines, kept alive only in conditions of extraordinary isolation. It would mean the strangeness is woven into the warm and ordinary stuff of living things, into the eye of a small bird, into the green of a leaf turning sunlight into life. The same physics that stirs in the hearts of stars, quietly at work inside a creature's body. There is something deeply moving in that thought, that the deepest mysteries of matter might not be far away and cold at all, but close and warm and alive, humming softly inside the things that breathe. A small robin sits on a branch on an autumn night, the air turning cold, a long journey ahead of it. It lifts into the darkness and turns without hesitation toward a direction it can somehow feel, guided, perhaps, by a faint flicker of quantum light painted across its vision, a compass made of the very same strange physics that lights the distant stars it flies beneath. It does not know how it knows. It simply turns toward home and flies on into the gentle dark. Even perfectly empty space is not truly empty and never truly alone. Picture the emptiest place you can imagine. A patch of space far out beyond the stars, in the great dark between galaxies, swept utterly clean, with no planet, no dust, no particle of matter, not even a single drifting speck of light. Pure nothing. We tend to think of such a void as the simplest thing that could possibly be. Sheer absence, a perfect blankness, an empty stage with nothing whatsoever upon it. If there is anything we feel sure we understand, it is nothing. Nothing, surely, is just nothing. But according to our best and most carefully tested understanding of how the world is built, even this perfect emptiness has a hidden life and a hidden structure. For one thing, the void is not still. The empty space of our best theories shimmers with faint, restless fluctuations, a ceaseless, gentle trembling woven into the fabric of emptiness itself. far too subtle to see, yet really there, the quiet breathing of the vacuum. Empty space is not a flat, dead blank, but something alive with a soft and constant stir. And there is something stranger still, and this is the heart of it. The emptiness is entangled with itself. Take two neighboring regions of the void, this small patch of nothing here, and that small patch of nothing just beside it. And they are not truly separate things. They are linked in that deep quantum way, their faint fluctuations bound together, sharing connections that reach quietly across the empty boundary between them. The nothing here and the nothing there are woven into one another beneath the surface of their emptiness. This is not a wild guess or a flight of fancy. It follows directly from our best theory of how fields fill space, the same well-tested understanding that underlies so much of modern physics. The vacuum in this picture is shot through with entanglement, stitched together everywhere by these unseen threads. And because the threads are real, to carve one region of the void cleanly away from its neighbor, to truly separate this nothing from that nothing, to cut every connection between them, would cost something. You cannot snip the threads for free. The emptiness resists being torn apart, because beneath its blankness it is genuinely, quietly whole. This humble fact, that empty space is entangled with itself, turns out to brush against some of the deepest questions in all of physics. It is tangled up with the strange discovery that black holes seem to carry an immense amount of hidden entropy, somehow written across their surfaces rather than packed inside them. And it touches the frontier dream. And here I must be clear that this part remains unproven and speculative, a frontier idea still being explored. That the very fabric of space itself, the smooth stage on which everything happens, might somehow be woven out of entanglement, built up from these countless threads running through the void. That last thought is far from settled. It lives at the very edge of what theorists are still trying to understand. But the simpler truth beneath it, that even empty space is entangled, rests on solid ground. Let yourself sit with how gently this overturns what we assumed. We imagine emptiness as the absence of everything, the one truly lonely thing, a void with nothing in it and nothing to connect, the very picture of separation and bareness. And instead, our best understanding whispers that even the void is connected to itself, stitched together beneath its emptiness, woven whole where we expected only blank and lonely space. The nothing is not alone. The nothing is held. There's something tender in that, if you follow it down into the quiet. We so often feel the universe to be a cold and empty place, vast stretches of dark separating every warm and living thing. And here in our deepest physics is a hint that even the emptiness between the stars is not truly empty, not truly divided, that the void itself is woven through with connection, holding hands with itself across every boundary, a fabric rather than a blank. A patch of empty space rests far out in the dark, beyond every star, silent and seemingly bare. No matter stirs there, no light, nothing at all that the eye could ever find. And yet, it is not nothing. It trembles softly with the quiet life of the vacuum, and it is woven through and through with gentle connections. The nothing here bound to the nothing just beyond it, threads too deep to see stretching across the empty dark. Even there, in the emptiest reach of all, the universe is holding itself together. Even the void is not alone. There is one last way to escape the strangeness of entanglement, and almost no one alive is willing to take it. Through all the careful experiments we have spoken of, the closing of every loophole, the sealing of every trapdoor, the decades of patient work confirming that distant particles really are bound in ways no ordinary explanation can capture, there has remained quietly a single logical escape, one final door that, strictly speaking, no experiment has ever been able to shut completely. And almost every physicist who has ever considered it has chosen to turn away because of what waits on the other side. To understand this last door, recall what the great test of entanglement quietly rests upon. The whole proof that two distant particles cannot simply be carrying hidden, prearranged answers depends on one assumption so natural we hardly notice it: that the experimenter is genuinely free to choose at the very last instant which question to ask each particle, and that this free choice has nothing whatsoever to do with the particles being measured. The choice and the particles are taken to be entirely independent, unconnected, strangers to one another. It seems obvious. Of course, the scientist's decision about which way to turn a dial has nothing to do with the secret state of some particle flying toward the detector. But what if that is not so? What if the choice the experimenter makes, the decision that feels so free, so spontaneous, so entirely their own, was in truth secretly tied all along to the very particles they were about to measure? Not by any signal passing between them in the moment, nothing so crude as that, but through a long chain of cause and effect reaching far back into the past, back through the experimenter's thoughts and body and history, back through everything that ever shaped that particular decision, reaching in principle all the way to the earliest moments of the universe. If the choice and the particles share a common root somewhere in that deep past, then the perfect correlations between distant particles need no spooky connection at all. The particles could carry plain, ordinary, preset answers, and the experimenter would simply always happen to ask exactly the questions that fit those answers. The whole experiment, in this view, would have been choreographed from the very beginning. The particles' hidden states and the scientist's free-seeming choice quietly arranged to match long before either one came to be. This idea is sometimes called superdeterminism, and I want to be very clear with you. It is a speculative and deeply unpopular position, one that almost no physicist accepts. It is mentioned here not because it is believed, but because it is the one logical escape that has never been fully closed, and because it is among the strangest thoughts the whole subject can offer. The reasons for the near-universal reluctance run deep. For one, this idea seems to demand an almost unimaginable fine-tuning of the entire universe, a kind of cosmic conspiracy woven into the very initial conditions of everything, arranging all the countless details of cause and effect so precisely that our experiments are forever and perfectly fooled in every laboratory, in every test without exception. That feels to most far too much to swallow. And for another, it would quietly undermine something that all of science depends upon without ever stating it: the assumption that we are free to choose what we investigate, that our experiments are not secretly rigged from the start to mislead us. If that assumption fails, the ground beneath every experiment ever performed begins to tremble. And so superdeterminism is regarded by the overwhelming majority of physicists as a last resort, logically possible perhaps, but so unwelcome and so strange that almost no one is willing to embrace it. A small handful of serious thinkers find it worth pursuing, Nearly everyone else gently sets it aside. But let yourself drift, just for a moment, into what it would mean if it were true. It would mean that nothing in the universe is ever truly random, and nothing is ever truly free. That every event, every flicker of a particle, every turn of a mind was set in motion together at the dawn of time, all of it threaded into a single unbroken pattern, reaching from the first instant to this one. It would mean that the spinning of the smallest particle and the choosing of the largest, most thoughtful mind are not separate things at all, but strands of one fabric, woven together long before either could know it. And it would mean, my friend, that even your choice in this very moment, whether to keep listening to these words a little longer or to let sleep finally come and carry you down, was perhaps not entirely yours to make tonight, but a thread set quietly in motion at the very beginning of everything. Whether the universe is truly woven that tightly, no one knows. Almost no one believes it, and perhaps no one ever can know for certain, since the very tools we would use to check are themselves part of the pattern we would be checking. It is a vast and ancient thought to carry down into the dark, that the turning of a particle and the drifting of a mind towards sleep might be the same kind of thing, set going together at the start of time. You need not decide whether it is true. You need not decide anything at all now. Let the question grow soft and distant, and as it does, the difference between choosing and not choosing, between holding on and letting go, blurs gently away, until there is only the quiet and the dark and the slow and welcome falling into rest. If you are somehow still awake, still drifting here at the edge of all these quiet mysteries, then know that there are other long journeys like this one waiting for you. Other nights, other corners of the universe to wander slowly through whenever you would like to return. There is always another stretch of darkness to explore, another wonder to fall asleep beneath. You need only come back when you are ready. But if your eyes have already closed, if you have slipped away somewhere among the entangled particles and the branching worlds and the gently woven void, then let them stay closed. There is nothing more you need to do tonight, nothing to solve, and nothing to hold on to. The mysteries will keep. They have waited a very long time, and they are in no hurry at all. Let the strange and beautiful universe go on turning softly without you for a while. Let the distant particles hold their secrets. Let the questions rest, unanswered and unhurried, until some other night. For now, simply rest. You are a small, warm, living piece of this vast and wondrous cosmos, and you have wandered far enough for one night. Sleep well, my friend, and sweet dreams among the stars.